Hello everyone, welcome to our presentation today. So our presentation is on the Henry David Thoreau footbridge. So here's a picture of the bridge, and right away from the picture we can tell that the bridge is a cable-supported bridge. So moving on, the location of the bridge is in Washington, Connecticut in the United States. The bridge is located in the Steep Rock Nature Preserve, and it spans over the Chappaqua River. The bridge itself was constructed to connect the North and South Trail with an attempt to enhance the natural beauty of the area around it and not take away from it. So let's take a closer look to the bridge. The bridge actually has fixed end supports, and these fixed ends have vertical forces and moment forces. The bridge itself does not take any horizontal force at all. By bridge itself, I mean the bridge deck. The cables, however, take all of the horizontal forces. So the cables have 11 hanger cables on each side of the bridge. They vary in length, and they can be drawn as roller support connections to the bridge deck. And for our roller assumption, basically what we can see here is how the cables connect to a bar that is underneath the bridge deck holding it up, and we assume the roller as it simplifies calculation. So as for the north end of the bridge, there is a 35-foot tower that tensions the cables, and the cables, when they go over the tower, they extend out to the back side of the tower into two helical pile anchors, which are about 25 feet apart, and those helical pile anchors transfer forces to datum, and it can take up to 150 kSI. The south end of the bridge, however, doesn't have a tower, but because of the cliff, the cables are able to extend into the cliff face, and those cables connect to helical pile anchors there. So the disassembling of the bridge. There are 50 pins, including ends, and there are 4 fixed ends. As for loading, our dead load would be the weight of the bridge decking, which is glulam beam. It would be 53 pounds per cubic foot. As for the live loads, what we chose for a normal loading would be a 200-pound person at every point of maximum moment, and our extreme loading, which would be a snow and ice distributed load across the bridge deck, which would have a density of about 25 pounds per foot cube. As for load placement, we need to find the areas of maximum moments in order to appropriately place our live loads. And as you can see from our diagram and through calculation, our maximum moment in this diagram was exactly between the reaction supports. So it was exactly in the middle of each beam. So as for our analysis of the North Tower, to find the tension in the cable and find the maximum tension, what we did was we treated the very first connection of the hanger cable on the mainline cable as a joint, and we treated the reaction force that goes upwards as tension in the cable that would go downwards. So basically the downward force in normal load would be 1,222.2 pounds, and in the extreme load would be 1,912.5 pounds downward. And so to find the tension that goes towards the tower, we just used the triangles. And so technically we're also able to find the tension that goes to the next cable as well, but because we already know that the tension in the cable that connects from the tower to the first hanger is the maximum tension, because we know that the maximum tension occurs at the very top of the near the very top of the tower. So our tension in that section for the normal load would be 1,511 pounds approximately, and for the extreme load would be 2,197 pounds approximately. So for our normal loading, as you can see here, we placed a person in the middle of each beam for the maximum moment. So our normal load is basically a point load. And our analysis for our normal loading was that we used the displacement method. And with the displacement method, we were able to find each of the reaction forces by finding the shears of each beam on the outsides. And by finding that, at the end, we were able to calculate the moment on each side of the beam. So with this, we found that on the normal loading, the reactions of the middle supports were 1,222.2 pounds in the upward direction, while the reactions on the outer supports were 661.1 pounds in the upward direction. The moment about A, which was the tower side, was 115,080 pound-foot counterclockwise, and the moment about the cliff side was 115,080 pound-foot clockwise. So for our extreme loading, as you can see here, when we were visiting the bridge, we were very fortunate to actually find snow and ice on the bridge so that we could actually just show examples on our presentation. So for the extreme loading, we basically just did the same thing, displacement method, except we just add another distributed load of the snow and ice mixture. And with that, we found that the middle reaction supports had 1,912.5 pounds upwards, and the outer supports had 956.5 pounds upwards. And with that, we can see that there is a drastic change of the forces of the reactions with the extreme loading scenario. And the moment about the tower side would be 81,870 pound-foot in the counterclockwise direction, while in the cliffside direction it would just be counterclockwise. So thank you very much. It was great talking to you today about the Henry David Thoreau footbridge. Another few things I wanted to mention is that the tension, the safe load for the cables are about 25,800 pounds, while the minimum braking load would be 129,200 pounds. So we know that our cables in the bridge are actually very safe and they can hold a lot more. So there's nothing to worry about with the cables. And the bridge is very well designed. And with that, thank you very much.